Welcome to Unit 2, Lesson 3, Solving Linear and Quadratic Inequalities. So an inequality is something that you probably haven't really experienced much of up to this point in your learning. But its name really tells you what it is. It's trying to represent a relationship between two things that are not equal to each other. So you're very used to equations at this point, where we have some sort of expression on the left side and some sort of expression on the right side, and an equation says that those two sides are equal to each other. Sometimes, though, we have two sides or two expressions that we know are not equal to each other, but we may still know which one is greater than the other or less than the other. And we can use that to try and solve or find other values that will continue to make that inequality true. So first, let's just think about how inequalities work in general. And again, this idea of inequalities is going to focus a lot on greater than or less than symbols. So first of all, just a little reminder for something like this. This is an inequality statement here. 9 is greater than 6. And there are different ways that you can use to remember the greater than or less than symbols. I still use a very simple one from my first grade teacher, which just said that we can imagine that the greater than or less than symbol is like a little alligator with his alligator teeth. Can't really draw them in that tiny right there, but has little alligator teeth, and the alligator always wants to open its mouth towards the larger value. So it is always trying to eat the larger value, and so it's always going to point towards the larger thing. So that means 9 is greater than 6. So that's an inequality statement, and hopefully we agree to begin that that is a true inequality. We know that 9 is greater than 6. But with equations, we know that we're able to do lots of tricks to equations and still have them be equal to each other. So if we have an equation, we know that we can add the same thing to both sides and the equation's still true. We know that we can subtract the same thing from both sides, or multiply by the same thing on both sides, or even divide by the same thing, and the equation is still true. The two sides are still equal to one another. Does it work the same with inequality situations? That's what we have to ask ourselves. So let's start with a statement that we know is obviously true, that 9 is greater than 6. And let's see what happens when we start to take each side of that inequality and make some changes. So for example, if we add 3 to both sides, well, if we add 3 on the left, that's 12. We add 3 on the right, that's 9. And well, yes, it's still true that 12 is greater than 9. So that inequality, or that greater than less than symbol, is still pointing in the same direction. We haven't had to change that inequality statement at all. It's still true. Let's try and subtract 3 from both sides of what we started with. So 9 subtract 3 is 6. 6 subtract 3 is 3. And the inequality direction still holds, that 6 is still greater than 3. So what that's telling you now is that we can add things to both sides of an inequality or subtract things from both sides of an inequality, and that inequality statement is still true. Whether it was greater than or less than, whichever it was, it still is going to be true and hold true. Let's try multiplying each side by 3, specifically positive 3. So that would be 27 and 18. And actually the inequality still points in the same direction. Yes, 27 is obviously bigger than 18. What about if we divide by 3 in each case? Well, 9 divided by 3 is 3. 6 divided by 3 is 2. So our numbers are much smaller, but it's still true that this direction still holds. 3 is still greater than 2. So that means we can multiply both sides by any positive number we want, as long as we do the same thing to both sides, and the inequality still holds. What about if we multiply by negative 3? Well, if we multiply by negative 3 on the left side, it gives us negative 27. And by negative 3 on the right gives us negative 18. But then we have to stop and be really careful, because now negative 18 is actually the greater number. So all of a sudden my inequality symbol flipped now from pointing toward the greater number on the left, and now the greater number is on the right. So something about the fact that this thing I multiplied by was negative seems to have flipped the sign of my inequality symbol. Let's see if that happens for division as well. Well, 9 divided by -3 is -2, and 6 divided by -3, or sorry, 9 divided by -3 is -3, and 6 divided by -3 is -2. And now we look at this one, and once again, we have flipped our inequality sign. So it's now switched to the opposite. So again, it's something about dividing, there's nothing special about the 3, but dividing by a negative and multiplying by a negative seems to be the only thing that flips our inequality sign. So what that means is that we can essentially approach inequality situations with the same bag of tricks that we use when we're solving regular equations. Like with equations, remember, we can add or subtract the same thing from both sides, and generally we can multiply and divide by the same things on both sides. The only difference now with inequalities is this statement here. When we're multiplying or dividing an inequality by a negative number, we have to change the direction of the inequality sign. But that's really the only new rule we have to remember. Everything else is going to still hold true and follow the same rules that we use for solving equations. So let's see how that works using actual mathematical expressions and try and figure out what our answers actually mean. Because this question is asking us to not just solve these linear inequalities, but to graph the solution on a number line. Now, you probably have no idea how to do that because you don't really know what solution to an inequality even means. Let's play around with the numbers a little bit first, and then we'll talk about what our answer really means. So this is more like an inequality statement that you'll be seeing throughout the rest of this course. We don't really need them for things like 9 and 6 because we know that 9 is greater than 6. We use inequality statements more so when there's variables involved. Essentially now, we're looking at this variable x, and instead of just trying to find one specific value for x, or maybe 2 or 3 specific solutions for x, we're trying to find a whole range of possible x values that overall will keep this left side less than this right side, or less than 11. So it's essentially asking, what are all the possible x values that if you multiplied them by 4 and subtracted 1, would always still be less than 11. Not equal to 11, but always less than 11. And we can solve that not just by doing weird guess and check, but by isolating x the same way we would if it was solving an equation. So remember, I can add 1 to both sides of an inequality, and I haven't changed the value of the inequality. So for example, 4x must be still less than 12. I've added 1 to both sides, and it's still true. And in our chart above, we also saw that we can divide both sides by any positive number we want, and the inequality is still true. So if I divide both sides by 4, I recognize that x now must be less than 3. So what it means to solve an inequality is to find a special statement in the end, like this one, that will represent not just one or a few different x values, but a whole possible range of x values that still keep the original inequality statement true. And what we're finding now is that as long as x is any number that's less than 3, then this original expression will be true. That's what we've found. The last piece, though, asked us to try and graph our solution on a number line. And when we say graph, you don't have to think of an x and y coordinate system. We're really just dealing with x values along a single number line. That's what we're really going to be graphing. So it's really important first to note that this symbol is just less than. So in other words, we're only looking at x values that are less than 3, but not 3 itself. So that means 2.9 is okay. 2.99 is okay. 2.999999999 is okay, but 3 is not. 3 is too big. So we really need to get every possible number included as close to 3 as we can, or infinitely close to 3, but 3 itself is just too big, so it's not included. So how do we show that on a number line? Well, I'm going to zoom in a little here on our number line. The way we show that is by putting an open circle or a hollow circle at the number 3. And that circle is sort of defining a special point that we're starting at. But 3 is not included, so I'm going to keep it open. So if we have an open or hollow circle, that means 3 is not included in the range of values that we want. If I filled that circle in, that would mean that 3 is allowed, or 3 is also included. And we'll see a situation like that in our next one. But this circle means that 3 is not included, but now if I draw a line down my number line in this direction, that's me graphing the statement x is less than 3. So again, it's not including 3, that's why I've left the circle open, but it's including every possible value less than 3, and that's why I'm showing my arrow going in that direction, all the way as far into the negatives as we could go. Let's try another one. Now we've got a little bit more complex stuff happening, but we tackle it in the same way. And when I say the same way, I mean, we think of it just like it was an equation. So if this was an equation that you were solving, even back in grade 9, you might have had an equation that looked something like this. It wouldn't have had an inequality sign, though. It would have just had an equal sign. But you would have recognized that you have to expand it out first. So 6 minus 3x plus 1 is still less than or equal to 13. So here's something that we need to make note of as well. This symbol here is not just saying that the left side has to be less than 13. It's saying that it has to be less than, or it could be exactly equal to 13. And that's what that extra little line underneath the less than symbol means. It means less than or equal to. But let's still solve the same way. This would be like negative 3x plus 7 has to be less than or equal to 13. I can subtract 7 from both sides, which tells me that negative 3x has to be less than or equal to 6. And now I have to be really careful, because to get x all by itself, so when I say therefore x and want to finish this off, I need to divide both sides by negative 3. But remember, when I divide both sides or multiply both sides by a negative number, it switches the sign of my inequality. So now I must say that x is greater than or equal to, and when I take 6 and I divide it by negative 3, I get negative 2. So because I was dividing by negative 3 on both sides, it flipped my inequality sign the other way. So this statement now, overall, is saying that any x value that's greater than negative 2 or equal to negative 2 will make the inequality statement that I started with true. So how do we graph that on a line? Well, once again, we start at negative 2, but in this case, it's okay if our answer is actually equal to negative 2. Remember in our previous one, we wanted everything less than 3, but not including 3. Now we can actually include the value negative 2. So we actually, instead of drawing just an open circle, we draw a filled-in circle, a full filled-in dot. And then all the x values we want are ones that are greater than that. So I draw an arrow that goes up the number line towards all of the greater values of x. And that's how I can graph, or in other words, represent visually what my solution is really telling me. So all of those values on the number line are the ones that make my inequality statement true. Let's keep going with these. For C now, same idea. It's just thinking of it the same way we would if this had been an equation. Well, when you're solving equations of this type, one of the first things you hopefully tried to do was get rid of fractions. So I'm going to take this whole thing, this whole inequality on both sides of it, and multiply it by, let's say, 4, because 4 is definitely a common multiple of both my denominators. So if I multiply everything on both sides by 4, I get 3k plus, well, this would be 2k now. And now I have to be careful because the other side's going to change as well. It's going to be 20. So in other words, now everything that I have on the left side has to be greater than 20. Well, 3k and 2k are just like terms. So just the same way we would if this was an equation, we'll collect the like terms and say that 5k must be greater than 20. And then I can divide both sides by 5. And because I'm only dividing by a positive number, I don't have to flip my inequality sign. So I can say, therefore, k must just be greater than 4, because that's what I get when I divide both sides by 5. So now if I want to represent that on my number line, well, I should also just recognize carefully that this is just greater than 4, but not equal to 4. So 4 is just a little bit too small, but 4.00001 or anything that's just slightly above 4 is totally okay. So we'll essentially start our graphing of the number line at 4, but we'll start it with an open circle because it includes everything slightly or infinitely close to 4 on the positive side or on the bigger side of 4, but not 4 itself. And then every other number from there going off in that direction. Let's try this one now. Again, same sort of idea. I'm going to multiply everything on both sides by something that will get rid of my denominators. Well, these would have a common multiple of 20. So I'm going to multiply everything by 20 on both sides. That's going to leave an extra factor of 4 multiplying with my numerator that I have on the left. And that's greater than or equal to, and I'll have an extra factor of 5 multiplying with my numerator on the right. And then here's where I have to be really careful. I can't forget that this also has to multiply by 20. So it's minus 20 on that side as well. Now I can expand out and simplify this, just the same way I would if it was an equation. Something like that. Or in other words, 4z minus 4 is greater than or equal to 5z minus 10. Now I'm going to subtract 5z from both sides. So I get negative z on the left side, and I'm going to add 4 to both sides so that I get negative 6 on the right. But now in my last step, I'm going to need to divide both sides by a negative, specifically by -1, if I want to think of it that way. So dividing by a negative, the only thing that that's going to do is flip my inequality sign. So if negative z is greater than or equal to -6, then positive z is less than or equal to +6. So again, because of this negative that I was dividing by, my inequality symbol had to flip at the end. So that means the values that I want include 6 itself. The exact number 6 is okay, and all numbers less than that. So I do a fully filled in circle at 6, and then I have my line that goes down in the, oops, I'll make it a little neater, down in the negative direction from there. So this one is going to look particularly strange because we have 3 separate pieces now, -3, 2x minus 1, and 5. And what's really happening here is that if we focus in and realize our variable is right here, our variable is sandwiched in this expression that is sandwiched in between 2 other sort of boundary points. So this expression in the middle, we're told, has to be greater than or equal to -3, but it also has to stay less than 5. So that's what makes this strange to deal with, is that we have these 3 separate pieces that we're dealing with and 2 inequalities symbols that are separating it all. But as long as we do the same thing to all 3 pieces, we follow all the same rules. So again, I'm trying to eventually figure out something about x. I want to get x all by itself. Well, right now it's also being subtracted with a 1. So what I'm going to do in my next step is I'm going to add 1 to everything. Add 1 to each of my 3 pieces. So it's -3 plus 1, 2x minus 1 that I originally had, plus an extra 1, and then 5 plus 1 as well. Or in other words, -2 is going to be less than or equal to 2x, which is less than 6. But again, I don't want to know what 2x has to be between. I want to know what x has to be between. So I need to divide everything, and I'll make a little note here. I'm going to divide everything by 2, all 3 pieces by 2. So -1 has to be less than or equal to x, which has to be less than 3. So overall, what is this really saying? Well, it's saying that the x values that keep this whole statement true have to be greater than or equal to -1. So they always have to be bigger than -1, or they could be exactly equal to -1. But then there's a boundary on how high we can go, because they always have to be less than 3 and never equal to 3. So they could go up again to like 2.99999 and however close we can get to 3, but never 3 itself. So x's that we're looking for are sort of sandwiched somewhere in between -1 and +3. So let's represent that on our number line. We'll start from -1, but we recognize that it also could actually be equal to -1, so I put a solid dot there. It's going to go all the way up to 3, but not including 3. So I can go all the way to the spot where I see 3 and put an open circle there, meaning that it's going to get as close as it possibly can, but it's never going to land exactly on that point of 3. And then it's going to include all of the values in between. And so we've represented that in this case, not with an arrow that extends infinitely down one way, but it actually just includes the points in between those values. Let's try one more of this type, but written in a bit different way. So now, instead of a variable that's sandwiched in between 2 other inequalities, what about if we actually have 2 separate inequality statements that we're trying to satisfy at the same time? Well, let's solve each of them separately and see what they tell us. So 2 minus k is greater than or equal to 5 is the first one. Well, if I subtract 2 from both sides, that tells me that minus k has to be greater than or equal to 3. And then I'm going to divide both sides by -1. So it means that therefore positive k, and I'm dividing by a negative now, so my sign has to flip. So k has to be greater than, or sorry, less than or equal to -3 now, because I divided both sides by -1. So that is one thing that has to be true for k. Or it has to satisfy this other one as well. So this other one could be that, well, if I subtract 2 from both sides here, -3k would be equal to -3. And then I want to divide both sides by -3. And oops, I put an equal sign there. That should not be an equal sign. That is less than -1. When I divide both sides by -3, I'm going to find what k is greater than now. And so it would be k is greater than +1. So now I have 2 things that I need to satisfy and demonstrate on my number line. I have to show k values that are are less than, but possibly also equal to -3. So let's show that one first. Well, so it could be equal to -3. I'll put a solid dot there because it could be equal to that. And everything less than that could be a value for k as well. So that's one branch of my overall solution. But I had this whole other branch that said that k could also be greater than 1. It just couldn't be equal to 1. It could be anything greater though. So because it can't be equal to 1, I put an open circle there, and it could be any value going off in that positive direction. So this, because it started with 2 separate inequality statements, is actually giving us 2 separate branches on our graph of possible k values that would satisfy it. So it could be k values from that left branch or those that come from the right branch. In the second portion of this lesson, we'll see how we can do this with quadratic inequalities by simply using a lot of the same skills that we used when we were solving quadratic equations.